Earth Systems 3209. Unit 3 Earth's Materials. Reference for Unit 3 Earth's Materials are seen in Chapters 2, Chapter 3, Chapter 6, Chapter 7 of the textbook, and also Appendix A and B of the curriculum guide. Unit 3, Topic 1.2. We'll look at mineral groups. Throughout the mineral group presentation, the focus will be on identifying and distinguishing between the main mineral groups that comprise Earth's crust. We'll also look at the focusing on identifying mineral groups based on their formulas. These questions are commonly asked as multiple choice, but not restricted to multiple choice on the public exam. The mineral groups that are found in Earth's crust. Minerals that form the rocks within Earth's crust belong to 7 main mineral groups. These are the silicates, carbonates, sulfates, oxides, halides, sulfides, and native minerals. If you look at the 7 different groups, you'll notice that 3 of the mineral groups end in ATE. This will have great significance later because the mineral groups that end in ATE, they all have oxygen in their chemical formulas. Then you'll see 3 of the mineral groups that end in IDE. 3 mineral groups that end in IDE will have significance because they all have metal in their formula with the addition of one of another element. We will discuss this in the upcoming slides. When we look at classifying mineral groups, there are several hints that we could use. Mineral groups that end with ATE have an oxygen group in its chemical formula and are one of the following. The first mineral group are called silicates. So again, if you see the mineral group ending in ATE, it means we have an oxygen group, but the element immediately preceding it will tell you which mineral group it belongs to. In this case, we see silica directly in front of the oxygen group, so it belongs to the mineral group silicates. The second mineral group we look at in Earth's crust, again, ends in ATE. Therefore, it has an oxygen group. The X in this case represents some number, O2, O3, O7, etc. But if we look at the mineral directly in front of the oxygen group, we see that it's sulfur. Therefore, sulfur in front of oxygen will give you the mineral group sulfates. The third mineral group, carbonates, ends in ATE. Again, it has an oxygen group. And you look at the mineral or the element directly in front of the oxygen group will be carbon. Therefore, it makes up the mineral group carbonates. So if you look over to the right, we see the first element, the first mineral that we're going to look at is called olivine. When we look at the chemical formula for olivine, we see the chemical formula for olivine is MgFe2 SiO4. So looking at the formula itself, we notice that it do have an oxygen group, O4, and if you look at the mineral or the element directly in front, it would be silica. So the mineral olivine belongs to the mineral group silicate. Second example we need to look at is one called barite. Barite, the formula is BaSO4. So when we look at the chemical formula, we see that it do have an oxygen group, O4. the element directly in front of the oxygen, in this case, would be sulfur. Therefore, if we got sulfur in front of the oxygen group, barite belongs to the mineral group sulfate. And from the name again, ATE suggests it has an oxygen group. And then your sulfur would be the element directly in front of the oxygen group. So let's look at the third example. We see we have calcite. The formula for calcite is CaCO3. We do have an oxygen group, O3. The element directly in front of the oxygen group is C, which stands for carbon. Therefore, calcite belongs to the mineral group carbonate. So the ATE in carbonate suggests it has an oxygen group. The element directly in front of the oxygen group would be carbon. And that is the hint that tells you which mineral group calcite belongs to. Let's look at the next series of mineral groups. Some mineral groups will end with the ending IDE, and that will give you a hint of which mineral group it belongs to. So mineral groups that end with IDE have a metal, okay, in its chemical formula, and are one of the following. They can be oxides, they can be sulfides, or they can be halides. So the ending of IDE suggests it has a metal as part of its mineral group, its chemical formula. So if we look at the examples above, oxides, basically you will see it has oxygen, or it could be an oxygen group. But if it has an oxygen group, we look at the element directly in front. If the element in front was carbon, then it would be a carbonate. If the element in front was silica, it would be a silicate. If it was sulfur, it would be a sulfate. But in this case, with oxides, the element directly in front of your oxygen or oxygen group is going to be a metal. And if it is a metal, then it belongs to the mineral group oxides. If we have sulfur in the chemical formula, there's no oxygen present, so we see sulfur in the chemical formula, and directly in front of the sulfur we see a metal. Then it belongs to the mineral group sulfides. And the third example of the ides is the halides. Halides basically identifies the main mineral as one of your halogen minerals. So on the periodic table, your halogen mineral group would contain chlorine, bromine, fluorine, which are the three common elements found in minerals. If we see chlorine, bromine, or fluorine in the chemical formula, and in front of this element is a metal, then we know that the mineral belongs to the halide mineral group. Let's look at some examples. First one, hematite. Hematite, when we look at chemical formula, is Fe2O3. In this case here, we do have an oxygen group. So one way we can look at it is we got to look at the element directly in front of the oxygen group. And in this case, it's iron. If it was sulfur, silica, or carbon, then it would belong to one of the eights. That would be silicates, carbonates, or sulfates. But seeing that we don't have one of those elements, and we do have a metal in front, it belongs to the mineral group oxides. The second example will be pyrite. Pyrite has the chemical formula FeS2. In this case, we don't have any oxygen group, but we do see sulfur. So therefore, we look in front of the sulfur, and we see a metal. And a metal in front of sulfur will tell us that pyrite belongs to the mineral group sulfides. In the third example, we have a mineral called fluorite. Again, when we look at the chemical formula, we do not see any oxygen group, but in this case we do see fluorine. And fluorine is one of the halides. In front of the fluorine is calcium, which is a metal. Therefore, we have a metal plus fluorine, which tells us fluorite belongs to the mineral group halides. So if we go and look at some of the characteristics of each of your mineral groups, we can first look at the mineral group silicates. Silicates are a group of minerals which contain silicon and oxygen as the most common elements. And these are the two most common elements found in the Earth's crust. Therefore, silicates will be the most common mineral group found in the Earth's crust. A mineral group that has silicon and oxygen as part of their atomic structure would be called a silicate. The most dominant mineral class in the Earth's crust would be the silicates, and they make up more than 96% of the Earth's crust. All silicate minerals have the same building blocks in common. And this building block, which forms the basis of all silicate minerals, is called the silicon-oxygen tetrahedron. It consists of 4 oxygen ions surrounding one small silicon ion in the middle. The diagram below demonstrates the silicon-oxygen tetrahedron. And if you notice, each of the oxygen atoms are the maximum distance away from each other as possible. This angle between oxygen atoms makes the tetrahedral structure one of the most stable chemical bonding structures there are. And this will give the silica tetrahedron, and therefore the silicate mineral group, some of the very unique properties when it comes to the properties of minerals. When we look at rock-forming silicates, the silicates are generally divided into 2 groups that make up the Earth's crust. The first group are called sialic silicates. Here we see sialic has Si and Al in its name. Therefore, we can conclude that the 2 most abundant elements, or common elements, in sialic silicates would be aluminum, which is Al, and the silicates would indicate silicon. So when we look at sialic silicates, they are rich in silicon and aluminum. They are the main rock type found in the Earth's continental crust. And they make up approximately 85% of the Earth's continental crust. These silicates are generally light in color. So in review, sialic silicates are rich in silicon and aluminum. They make up 85% of the continental crust, and they are light in color. When we look at the second group of silicates that make up Earth's crust, they are called the cymatic silicates. Cymatic silicates are rich in silicon and magnesium, and they also contain iron. Hence, the name ferromagnesium silicates, ferro standing for iron, and magnesium standing for the magnesium. They are the main rock type found in the ocean floor, and they make up less than 15% of the Earth's crust. And these minerals are generally dark in color. So, in review, when we look at cymatic silicates are generally made up of the elements silica, magnesium, and iron. They make up approximately 15% of the Earth's crust, mainly found in the ocean floor. And they are generally dark in color. These are the three main properties of cymatic silicates. When we go and look at some of the other mineral groups found in the Earth's crust, we see a second abundant mineral group are called the carbonates. Carbonates consist of atomic structure of one carbon surrounded by 3 oxygen atoms. And in chemical formula, we usually see CO3 as a part of the formula. The most common carbonate is calcite, which make up the rock limestone, and the chemical formula for limestone will be CaCO3. Another mineral group found in Earth's crust are the sulfates. These are compounds consisting of an atomic structure of 1 sulfur atom surrounded by 4 oxygen. The most common rock found in the sulfate mineral group would be gypsum. It also takes on the mineral name gypsum and has the formula CaSO4 2H2O. So it is a hydrate that is mainly made up of calcium and sulfate. The fourth mineral group found within Earth's crust are oxides. Oxides are compounds consisting of an atomic structure of oxygen combined with 1 or more metals. The most common oxides are those found of iron and aluminum. And these oxides are commonly called or referred to as ore minerals. Oxides found with iron, one of the most common would be iron oxide, which we call iron ore, which is currently mined at many points in the world, but in Newfoundland it is mined in Labrador City, and in the past has been mined on Bell Island. Also, we have aluminum oxides, which form some of our most precious gemstones, such as rubies and sapphires. Another mineral group found within Earth's crust are the halides. Halides, such as halite, is the most common halide, and they're made up of one of your halogen elements combining with a metal. The 3 most common halogens would be fluorine, chlorine, and bromine. Ooh, this is bad. Okay, so you have fluorine, chlorine, and bromine combining with a metal. They form your mineral group called halides. The 6th mineral group that's found within the Earth is called sulfides. Sulfides are compounds consisting of an atomic structure of 1 or more metals combined with sulfur. Sulfides also make up some of your mineral groups that are commonly called ore minerals. Some examples include pyrite, galena, and sphalerite. All 3 of these ore minerals are mined for the element that's contained in the formula. For example, pyrite is mined for iron, Fe. Galena is mined for the lead, Pb. And sphalerite is mined for the zinc, Zn. And the 7th mineral group that's found in the Earth's crust are your native elements. These are classified as native minerals. Native minerals exist as elements that occur uncombined in nature. They are in pure form, pure elemental form, and they commonly are called native elements. Some examples of your native minerals, which exist as native elements, would be gold, silver, copper, and sulfur. Let's look at some of your native minerals that we find, or actually, let's look at some of your chemical formulas that are used to classify mineral groups. Pyrite. If you look at the mineral pyrite, we see that its chemical formula is FeS2. We see here we have sulfur, and in front of the sulfur we have a metal. So here we have sulfur plus a metal, and that would put it into the mineral group sulfides. So pyrite is classified as a sulfide. Look at example number 2, hematite. Hematite do have an oxygen group, but when we look in front of the oxygen group, we do not see silicon, we do not see carbon, or we do not see sulfur. Therefore, they cannot exist as one of the sulfates, carbonates, or silicates. What we do see is a metal. So in this case, we have oxygen plus a metal, and oxygen plus a metal will form a mineral group called oxide. So hematite falls into the mineral group oxides. When we look at the mineral olivine, we look at the chemical formula. We have MgFe2SiO4. Here we do have an oxygen group, and if we look at the element directly in front of the oxygen group, we will see silica. So silica plus oxygen will classify olivine in the mineral group silicate. Example number 4, we have fluorite. We do not have an oxygen group in the chemical formula for fluorite. We have CaF2. So here we see fluorine, which is a halogen. In front of the fluorine, we have calcium. Therefore, calcium, which is a metal plus a halide, or a halogen element, will be classified as a halide. Pyroxene do have an oxygen group. Again, we look directly in front of the oxygen group, and we see silica. So silica plus oxygen would classify pyroxene in the silicate mineral group. Example number 6, we have calcite, which has oxygen. Directly in front of the oxygen, we have carbon. Therefore, carbon plus oxygen will classify calcite as a carbonate. Next one, gypsum, number 7. We do have an oxygen group, okay, in the chemical formula for gypsum. Directly in front of the oxygen, we see sulfur. So sulfur plus oxygen will be classified in the sulfate mineral group. Halide, we see the chemical formula NaCl. There is no oxygen group here, but we do see a halogen element, chlorine. Immediately in front of the halogen element is a metal, so metal plus a halogen will classify halide into the mineral group halides. Corundum, which has the chemical formula Al2O3, we do have an oxygen group. In front of the oxygen, we see aluminum. Therefore, aluminum is a metal, so a metal plus oxygen would form in the mineral group oxides. And last would be cinnabar. Cinnabar is a mineral that's made up of mercury and sulfur. So again, we do not see an oxygen group, but we do see sulfur. And in front of the sulfur, we have mercury, which is a metal. So mercury plus a metal will classify cinnabar in the mineral group sulfide. So in review, when you look at the mineral groups, very first thing you should look for do it have an oxygen group? If it has an oxygen group, we're looking for the element directly in front. If it's carbon, silica, or carbon, silica, or sulfur, carbon, silica, or sulfur, then it belongs in one of the three mineral groups that end in ATE. So carbon with oxygen would be a carbonate, silica with oxygen would be a silicate, and sulfur with oxygen would be a sulfate. If we don't see either one of these elements, but we see a metal in front of the oxygen group, then a metal plus oxygen will belong to one of the mineral groups that end in IDE. So if it's a metal with oxygen, it would form the mineral group oxide. If we don't see any oxygen in the chemical formula whatsoever, but we do see sulfur with a metal in front, then a metal plus sulfur would be a sulfide. And lastly, if we see one of the halogen elements, Cl, F, or Br, plus a metal, they belong to the mineral group halides. Let's look at some examples. First example, it reads, which is a sulfate mineral? So if we look at the mineral group, we see we have a sulfate mineral. ATE suggests it has an oxygen group, and sulfur would be located in front of it. So we're looking for a chemical formula with SO, usually 4, but it could be SO7, SO3. So if we look at our choices, we got our first choice is calcium, magnesium, CO3, 2. So that wouldn't fit into the sulfate mineral group. But if we look at choice B, we do have an oxygen group with a sulfur element in front of it. So B would be the correct answer for this question. Which is a sulfate mineral? And the answer will be B, based on its chemical formula. Example number 2. It says, to which mineral group does CaCO3 belong? So if we look at the chemical formula here, we have CaCO3. We do have an oxygen group, in this case O3. The element directly in front of your oxygen group is carbon. Therefore, carbon plus oxygen will give you the mineral group carbonate. So the answer to this question would be A, carbonates. Your turn. Take the time and complete the following question. The answer will be on the following slide. So you can stop your recording now and answer the question, which is an example of a halide? Now that you have time to prepare your answer, which is an example of a halide? If you have a halide, therefore, halide itself suggests that you have one of the following elements: fluorine, chlorine, or bromine, combined with a metal in front. So if we look at our chemical formulas here, we have an oxygen group, so that wouldn't fit into the halide mineral group. We have an oxygen group in choice B, which wouldn't fall into the halide mineral group. We also have oxide or oxygen group in choice D, which would not fall into the halide mineral group. But when we look at choice C, fluorite, CaF2, we do have our halogen followed by a preceding metal, would be C. In summary, let's look at the overview of the points covered. Minerals that form from rocks from the Earth's crust belong to 7 main mineral groups. If you look at the silicate minerals, all silicate minerals will have in common silica and oxygen. So if you have some form of silica and oxygen in the chemical formula, they fall into the silicate mineral group. Carbonates will have carbon and an oxygen group. Sulfates, sulfur with an oxygen group. Oxides contains a metal followed by an oxygen group. And then when you get into halides, halides would have an halogen element, a metal, followed by one of your halogens, either fluorine, chlorine, or bromine. Sulfides would have a metal, followed by sulfur, and your native elements would have pure elements. And some of the examples include gold, carbon, which is diamond, copper, sulfur, and silver.